Data Science Analysis and Applications in Medicine Part 1, number 1562, the 6th of March 2026. Gerald C. EclaireMD Foundation. Category: Medical Data Science. Introduction. In modern medicine, most clinical decisions are still based on limited data points collected during occasional clinic visits. A physician may measure blood pressure once during an appointment, review a laboratory report every few months, and then make treatment decisions based on those isolated measurements. These observations are essentially snapshots. While useful, they often fail to capture the dynamic behavior of the human body. My approach to medical research is different. It originates from my training in mathematics, physics, engineering, artificial intelligence, and system analysis. Instead of viewing physiological measurements as isolated numbers, I treat them as signals generated by a complex dynamic system. Over many years, I have collected large amounts of personal pathophysiological data, including body weight data, glucose measurements, blood pressure readings, sleep patterns, physical activity levels, and both quantitative and qualitative dietary information. These 4 million data points allow me to observe the continuous evolution of complicated biomedical processes. In this framework, pathophysiological data are not merely numbers, they are stories, like a movie, describing how the body responds to internal and external stresses over time. Deterministic thinking and biomedical systems. My scientific philosophy begins with the belief that natural systems are fundamentally deterministic. Biological processes follow physical and biochemical laws. When certain inputs occur, corresponding pathophysiological responses follow. This cause and effect relationship allows researchers to build mechanistic models of various diseases. For example, repeated metabolic stress such as obesity and diabetes can gradually damage vascular structures. Over time, these metabolic stresses accumulate mechanical and biochemical effects that eventually lead to clinical events such as stroke, cardiovascular disease, or renal disease. From an engineering perspective, this process resembles a structural system under repeated load, where cumulative stress eventually leads to material fatigue or rupture. Because of this deterministic viewpoint, my primary analytical tools come from engineering and physics. I have developed and applied a framework known as viscoplastic medicine theory (VMT) model. In this approach, physiological stressors are treated as mechanical loads acting on biological structures, and disease progression is interpreted as the gradual deformation of these biomedical structures over time. Another important analytical concept is topology. Instead of focusing only on individual measurements, topology examines the overall shape, patterns, and connectivity of data points. Biological signals, such as blood pressures, high-frequency waves, glucose levels, medium-frequency waves, and body weights, low-frequency waves, often fluctuate due to noise or measurement variation, but their overall structure frequently remains stable. Topological analysis allows researchers to recognize meaningful geometric patterns even when individual measurements vary. Different wave behaviors in pathophysiological data. Many physiological signals behave like waveforms. Blood pressure, glucose levels, and heart rate all fluctuate continuously over time. When examined as time series, these signals display characteristics similar to those found in classical wave theory. Important wave features include amplitude, frequency, period, and waveform shape. From a physics perspective, physiological signals behave like dynamic waves that can be analyzed in both the time domain and the frequency domain. The time domain describes how the signal changes over time, while the frequency domain describes the rate and pattern of oscillation. These wave properties provide important clues about the underlying regulatory mechanisms of the human body. For example, blood pressure does not remain constant. Its frequency unit is measured in seconds, and it oscillates with each heartbeat. In addition, it responds to respiration cycles and varies according to circadian rhythms across the day. Sudden spikes may reflect emotional stress, pain, or physical activity, while gradual shifts may indicate metabolic, neurological, or vascular regulation. From a frequency domain perspective, blood pressure therefore contains multiple superimposed oscillations, including cardiac frequency, respiratory frequency, and slower circadian components. Glucose also does not remain constant. Its frequency unit is measured in minutes, and it oscillates with food digestion, physical activity, and the duration and intensity of exercise. After meals, glucose rises and falls in a characteristic wave pattern driven by digestive absorption and insulin response. Exercise introduces additional oscillations depending on energy consumption and muscular activity. Body weight changes more slowly. Its effective frequency unit is measured in hours. And it fluctuates with food intake, water consumption, bowel movements, sleep, and other daily physiological processes. Compared with blood pressure and glucose, body weight behaves as a lower frequency physiological signal because the underlying mass balance processes operate over longer time scales. Taken together, these physiological variables form a multi-scale dynamic system. Blood pressure reflects second-level oscillations, glucose reflects minute-level oscillations, and body weight reflects hour-level oscillations. Understanding these signals as wave processes allows researchers to analyze human physiology using the same wave theory principles applied in physics and engineering systems. From an engineering and signal analysis perspective, these physiological waves can also be interpreted using Fourier thinking and spectral decomposition. Fourier analysis states that any complex waveform can be represented as the sum of multiple simple sinusoidal components with different frequencies and amplitudes. When applied to physiological signals, this concept means that measured variables such as blood pressure, glucose, or body weight are not single signals but composite signals composed of multiple overlapping oscillations. For example, a blood pressure waveform contains a high-frequency cardiac component generated by each heartbeat, a respiratory component linked to breathing cycles, and lower-frequency components associated with autonomic nervous regulation and circadian rhythms. Similarly, glucose fluctuations contain post-meal digestion waves, exercise-induced metabolic waves, and slower endocrine regulation components. Spectral decomposition allows these overlapping signals to be separated into their frequency components, making it easier to identify the underlying physiological mechanisms driving the observed waveform. This approach provides a powerful analytical bridge between engineering signal processing and biomedical physiology, allowing complex biological behaviors to be interpreted as structured wave systems rather than random fluctuations. Clinicians often interpret blood pressure as a single number, such as systolic pressure measured during a clinic visit. However, from a signal analysis perspective, the pattern of fluctuations may reveal much more information than any single measurement. Most clinicians lack mathematical training in these areas. As a result, it is difficult for them to trace pathophysiological behaviors at this level of depth or gain similar insights into the underlying mechanisms. Because of my background in mathematics, physics, and engineering, I tend to recognize waveform patterns almost instantly. When viewing a dataset, I do not analyze or process each number independently. Instead, I subconsciously see the overall picture, structure, or graph of the signal and the direction in which the system is moving. This pattern recognition ability allows me to identify potential pathophysiological risks much earlier and more quickly. This is part 1.